Hello, I am Brandon, and welcome to the next video in my series on basic statistics. If you are new to the channel, welcome. If you're a returning viewer, it is great to have you back. If you like the video, please give it a thumbs up, share it with classmates, colleagues, or friends, or anyone else you think might benefit from watching. So now that we know each other, let's go ahead and get started. So this video is the first in a new series, and this series is about nonlinear regression. So in a previous series, we talked about simple linear regression, but simple linear regression isn't always the best option or the best model for our data. Not all data follows a straight line. So in this series, we'll talk about nonlinear regression basics. We'll talk about things like overfitting and diminishing returns and things like that. So this video is about the very basics of nonlinear regression, and we'll get to more advanced stuff as we go. So I'm excited about this new series, so let's go ahead and get started. So this video is brought to you by the great people at the Great Courses Plus. Chances are you are watching this video because you either have to, want to, or need to learn something. And there are a few better places to learn about pretty much anything than the Great Courses Plus. They have over 10,000 video lectures on anything from math to photography to literature, history, pretty much anything you can imagine, yes, including statistics. So please see the link in the description below where you can get a free trial to the Great Courses Plus, and of course support this channel and support them. So let's go ahead and start learning about nonlinear regression. So here is our new example, Buckley's used cars. So Jack Buckley has owned a large used car lot outside of Melbourne, Australia for over 30 years. As a business person, he likes to keep track of how many cars a salesperson sells per week. So Jack would like to examine the relationship between how many total cars have been sold by each salesperson and how many weeks each salesperson has worked for Buckley's used cars. So basically, Jack Buckley wants to create a model where he looks at how long someone works or has worked for the company and then how many cars they sold over their time there. So what is our goal? We want to produce a model that minimizes error, but will also be good for new data. So what we want to do is produce a model that fits the data very well, but not too well. And we want to make sure that when we throw new data at it, that it does a good job of predicting data that is beyond the scope of the data we have to use. So that's kind of our goal long term. So here is our data. We can see that the first salesperson worked at Buckley's used cars for 168 weeks and sold a total of 272 cars. So more than one car per week, which is pretty good. The second person, however, worked there 428 weeks, but only sold 300 cars, so less than one per week, and so on and so forth. So as always, the first thing we do is graph our data. So we create a scatter plot, and this is what it looks like. So you can see we have the job tenure in weeks along the x-axis. That's our independent variable, and then we have the total cars sold on the y-axis, which is our dependent variable. So let's look at the scatter plot. Does it look linear? Does it not look linear? Well, I mean, I can see both, right? I mean, if you put a straight line through that data, it probably fits pretty good, but maybe it doesn't. Who knows? So again, this is the whole point of this video series, is figuring out which model best represents this data. So let's test some things out. So here's our data with a linear model on it. So you can see by looking at it that the straight line fits the data, pretty well. Okay, it kind of goes right through the data there. Nothing too crazy looking. We have a regression equation of 0.5823x plus 114.5. So again, if we kind of take the intercept aside for a moment, I'll talk about that later, we can see that for each week a person is at Buckley's used cars, additional week, we would expect them to sell a little bit more than a half of car per week. Now, of course, they can't sell a half a car, but well, I guess they could. But that's what we would expect. So for every week a person works there, we would expect the number of cars they sell to increase by 0.58 or 0.58 cars. So note, this may be a rare case where setting the intercept to 0 makes sense. So if someone has not worked there at all, they have sold 0 cars. So in most cases in regression, we don't really care about where the intercept is per se. But in this one, it might make good sense to actually set it to 0. However, for the sake of this example, I'm just going to leave it as is. But I just wanted to point out the obvious fact that someone who has not worked there cannot sell any cars, and therefore the intercept would probably be more appropriate in real life at 0, 0. But again, we'll leave it as is for now. So what about our linear regression output? So we ran this through Excel or something else and we get some regression output. So a couple of things. So our multiple R there is 0.8955, that's very high. Our R square is 0.8019. So this model explains about 80% of the variance in the dependent variable. So what we can say is that the number of weeks a salesperson is at Buckley's used cars explains about 80% of the variance in the number of cars they sell. So it's a pretty good explainer of the variance in our model. We can see that the standard error there is 45.94. Remember, that is sort of a measure of how well the observations fit around the regression line. So down here in the ANOVA table, that we can see that we have a total sum of squares of about 138,000 or so. So pay attention to that. We have a mean square of 111,000, a mean square error or residual of 2,110. That's pretty low relative to the total sum of squares. That creates an F statistic of 52.63. That's very, very high. And you can see that our significance value is very, very small. So the model is statistically significant. So down here at the bottom, we have our intercept and dependent variable. So there are the coefficients we saw earlier in a regression equation, the standard error for each, the p-value and t-statistics for each, which are both significant. And then we have the confidence interval. So at first glance, this looks like a pretty good model. But is this the best model? So let's examine the residuals. So let's look at some residuals. So here along the bottom, we have the predicted cars sold, and then the residuals over here on the y-axis on the left. Let's go ahead and plot the residuals. And here they are. So let's look at this for a second. Do we see any pattern here? Are the residuals evenly spaced out top to bottom, side to side? Is there sort of a triangle shape from one side to the other? So is there non-constant variance across the predicted cars sold? Or is there any curvature? So is it bending up or down or anything like that? So let's take a good look and see what we think. So here are our residuals with what I think is obvious. Our residuals fit a curvature. So we can see that we have residuals that are in the lower left of our graph here, and then they go up towards the middle. There's an empty space down here at the bottom middle, and then they go over and then down to the right here on the right side. So we should pause here and think about what potential problems we might have. Our residual assumptions are violated. So we have non-constant variance side to side. We have residuals lower left, they go up, and then they go down. So we don't have the optimum pattern we're looking for, and that should concern us when we're talking about finding the best model for our data. So because of our concern about the shape of our residual plot, we're going to add a nonlinear model. So there are several things going on here in this plot. So first we have our linear model. That's a black line that goes from lower left to upper right. And then we have our predicted cars sold in the sort of orange squares along that line. The red line is a polynomial. It's a quadratic model. And we'll get to what that means here in a second. So look at how that model fits the data a bit better. So remember, the orange diamonds, those are our actual observed points. So that polynomial or quadratic model kind of starts in the lower left, goes up, and then tails off over here on the right. So it would seem that that red line, the quadratic model, seems to fit our data better than the straight line there in the middle. So let's go ahead and examine that more computationally. So the nonlinear model. So based off the original scatter plot, and even more so the residual plot, it appears that a linear model is not the best choice to model the data. There is too much reducible error. The straight line regression is too far from the actual observed points from side to side. So there's an error in there that we could reduce further by having a better fitting model. The residual plot shows a definite curvature. So a linear regression model would not be the best choice or the appropriate choice for the data. So this indicates that the best model may be nonlinear. So polynomial regression adds extra independent variables that are powers of the original variable. So in this case, the weeks on the job was our independent variable, that's x. So what polynomial regression does is add powers of that as other variables. So x squared, x cubed, so on and so forth. That is polynomial regression. So first we have the quadratic model, which is the simplest. So we now include in the model the square of the independent variable, which is x1 squared. This will allow our model to capture the curvature in our scatter plot, in our original scatter plot. Quadratic models are pretty flexible, since higher order models such as the cube, or to the fourth or fifth or whatever, can be inserted in the model. It's pretty simple to do. However, careful. Adding terms can lead to overfitting. Now, I'm going to do an entire separate video on overfitting because it's a very important topic in many things in statistics, data science, and machine learning. But adding additional terms can just lead to overfitting, and therefore we have to be important about just dumping in more terms over and over again in the quadratic or in the polynomial model. So here's our original data. So weeks on the job and cars sold. Now we're going to add a squared version of weeks on the job. And this is what this looks like. So here we have a quadratic. We've taken the first variable and squared it. Now we have two columns of data, and one is just sort of a derivative of the first. So this is our new data we're working with. So now let's actually use software to do another round of output. And this is what we have. So we have a multiple R of 0.9526, that's very high. We have an R square of 0.9075. That's higher than the simple linear regression model. We have a standard error of 32.67. That's quite a bit lower than we had in the linear model. Down here in the ANOVA table, notice that we have the same sum of squares. So choosing a different model doesn't affect the total sum of squares in these instances. So total sum of squares is the same. So our mean square, 62,862. Our residual or error sum of squares is 1,067. If you remember, that's about half what it was in the linear model. And of course, the F is very high, significance is very low and it's significant. So if you go to the coefficients, you'll see that when we make a regression equation, we have a coefficient for weeks on the job, then of course weeks squared on the job, or weeks on the job squared down there in the lower left. You can look at our standard errors, our t-statistics, and our p-values. So it's important to note here that the p-value for both weeks on the job and weeks on the job squared are both significant. They are both 0.003, 0.0005, or whatever it is, so they are significant. Now I want to point out the sign of each one. So the coefficient for weeks on the job is positive, 1.4. The coefficient for weeks on the job squared is negative, and that will be important here as we go forward. So overall, this is a much better fit than the linear model. So our R squared is quite a bit higher, our standard error is quite a bit lower, our mean square error is about half of what it was, and then both of our coefficients are significant. So everything here looks pretty good. So linear versus quadratic. Let's take each one of these step by step. So here's the output for our linear model. So R squared, standard error, and so forth. And here it is in our quadratic model. So you can see the change. So our R square went up by 0.1, which is a pretty big jump in the explained variance. So this model over here on the right, the quadratic model, explained 10% more variance in the dependent variable than the linear model did. Then we have our standard error. So 45.94 in the linear model, and then 32.67 in the quadratic model. So again, what that means in sort of layperson terms is that in the quadratic model, the observed values fit tighter around the curve or the line of the quadratic model. So standard error is very helpful when comparing different models for the same data. So the higher R square and adjusted R square, which indicates more variance, is explained in the quadratic model. The lower standard error in the quadratic model indicates the observations fit tighter around the quadratic regression line. So how about the ANOVA tables? So again, a couple of things to notice. Sum of squares is the same, but how that total sum of squares is partitioned is different. So you can see that the residual sum of squares in the linear model was 2100 or so, and in the quadratic model, it's under 1100. So it's about half what it was in the linear model. That's very important. We're trying to reduce the error on our model by having a model that fits the data better. And here you can see evidence of that in the output. So note the significant decrease in the MSC in the quadratic model. Also note the SST is the same in both models. So what about the intercept and the regression lines? So here's our linear model. You can see that there. And here we have the quadratic model, which is there. So again, we just create the regression equation like we would any other time with the coefficients and the intercepts. So there they are. So in the quadratic model, since both the original and squared term are significant, it confirms the nonlinear relationship between the two variables. So the fact that our weeks on the job squared is significant indicates that this is a nonlinear model. So here are the two back-to-back, kind of blown up nice and big. So you can see that the linear model over here on the right, that's the black dotted line. That's a regression equation. We have an R-square of 0.8019. Here in the quadratic model, we have that squared term in there. You can see that at the beginning, and our R-squared is 0.9075. So again, you can see how the red line, the red curved model, fits the data better than the straight line. So now let's look at residual plots. Remember we did that back at the end of the simple linear regression video series. So now we have to figure out if this model is good based on the residuals. And here they are. Well, look, the residuals are a non-pattern. So there's no concerns here. The residuals are consistent as you go from left to right. They are apparent on both the top and the bottom of the residual plot. There's no curvature to them. There's no triangle shape indicating non-constant variance across. So this is a great residual pattern that we'd be happy with. So in this plot, we have several things going on. I'll do them one by one. First, we have the cars sold model. So we're graphing our weeks on the job, which is again our first independent variable, along with the observed values of the cars sold. So you can see over here on the right, we have the polynomial model for cars sold, and then we have the orange diamonds, which are actually the observations. Now on top of this, we're going to model our predicted cars sold. If you notice, it falls right exactly on top of the cars sold model. So now we can compare where each observed value falls in relation to the predicted values. And of course, because our model fits the data better, these residuals are going to be smaller. So here is our squared term. So again, we have the quadratic model applied to our cars sold. That's the red dashed line. And then we have the cars sold there in the orange diamonds. And then we're going to put that on top of the predicted values. You can see there, and you can see they're very close. So the fact that both the original term and the squared term were both significant in our output can be seen in the last two graphs. So when we actually model them, you can see that they fit very well. So here's our quadratic model overall residuals, not the individual terms that we saw in the last two slides, but overall. And there they are. That's great. That's a beautiful pattern. There is nothing odd about it. There's no curvature to it. There's no triangularity to it where one end is wider than the other, indicating non-constant variance. This is exactly what we want in residuals. So a few final notes. In this example, the nonlinear quadratic model was a much better choice. It fit the data better, the error was reduced, and it produced a nice set of residuals. The residuals from the linear model indicated a curvilinear relationship between the original two variables. That's a problem. We're trying to force data that is curvilinear into a linear pattern, and that can increase error and cause other problems in interpretation. So implementing a nonlinear quadratic model accomplished several things. It explained more variance. So remember that our R-squared went up by quite a bit. 10% more variance was explained in the quadratic model. We had a tighter fit of the observations around the regression line, so our standard error went down significantly. We reduced the model error. So if you remember, the mean square error was literally cut almost in half. And of course, we had a residual plot that no longer had a curvilinear shape. It was a nice non-pattern. The residuals were scattered everywhere, nice and neat, no curvature or no triangularity. And this will also naturally lead to better confidence and prediction intervals. So because the model is more appropriate, because it fits better, because the error is reduced, we're going to be able to make better confidence and prediction intervals than otherwise we could in the linear model. This video is brought to you by the Great Courses Plus, where you can get unlimited access to over 10,000 different video lectures taught by award-winning professors from the Ivy League and other top schools around the world. You can learn about anything that interests you: science, literature, and yes, statistics, like this lecture from Professor Talithia Williams called Regression Predictions and Confidence Intervals from her course Learning Statistics, Concepts and Applications in R. And right now, the Great Courses Plus is offering my viewers a free trial and is also now optimized for Australia and the UK. So go to thegreatcoursesplus.com/Brandon Foltz, my name, to have access to the over 10,000 video lecture library, or click on the link in the description below. Okay, so that wraps up this first video in nonlinear regression. So again, we're just trying to get the basics down, understand why a nonlinear model, or a quadratic in this case, will be better than a linear model when the data points in a certain direction. We talked about error, we talked about better fit, we talked about residual patterns. So again, this will carry over into other things, but I just wanted you to kind of understand and put together the concept of linear regression, residuals, and nonlinear. Look at the output and see how it all fits together. So I hope you enjoyed this video, and I look forward to seeing you again in the next one. Take care.